Well, here I am again. I was not planning on giving this lecture here, and it's not about acoustics. I prepared it for the ETMM meeting, which is next week. And so DNS and RANS modeling, it's a little bit one half of my life and the other half. And I'm trying to understand the relationship and what can DNS contribute to RANS modeling. Some of it will be historical and some of it looking at the future. Many of the figures were made by Gary Coleman of NASA and Andre Garbarek, who is here. So for the outline, so DNS obviously is a source of data for modeling. Its great advantage over experiments is that we have complete information on the flow. And so there are, many things that we cannot measure, but we can calculate. The potential could be to contribute new ideas. And I'll show an idea that is in the SA model that came from DNS in a sense. Potential, of course, to calibrate existing constants, not new ideas, but existing ideas, but improving them. And there's also validation of a full model. I'll show an example of this. The limitations of DNS, of course, are Reynolds number and geometry. And then I will go into what I call puzzling findings in DNS on the Karman constant, and then Lucchini's theory. So I will come to that. Maybe a new idea is what I call structural conflicts inside RANS models that happen in the log layer, and also questions of Reynolds number. Then look at how DNS can contribute to complex turbulence models, and then more simple turbulence models. Then one slide about artificial intelligence, where what I think we may be able to do with that. Okay, so this is talking about my own work in two ways. Here I'm showing on the left the budget of the Reynolds shear stress, which in a boundary layer is the dominant one, is the most important one. And from my DNS, what I found is that this budget is away from the wall is completely dominated by production and then the pressure term. And so this pressure redistribution, which tries to make the turbulence more isotropic so the shear stress is weaker, is very strong, and it's also attributed to the wall. We believe that the turbulence is limited by the presence of the wall. And so on the right, I show the budget of the eddy viscosity in the Spalart-Almaraz model. And there's production. And if you add together destruction term and the diffusion term in the wall region, they completely oppose the production, just like the pressure term. And so this was not quantitative, but from my DNS work, one idea went into the SA model, and it's an idea that is very important. Also, of course, Professor Sekundov had the destruction term long before DNS. He had it in the 70s in his new T model. So for me, this is where the idea came from. For Sekundov, it was more physics, intuition. So this is an example of an idea that you can say came from DNS. Here is an example of a validation. The paper by Hanyalik, Yakielish, and Hadzish in '93. And with Baldwin at NASA, we had done simulations of an oscillating boundary layer where the edge velocity was cosine omega t times u0. So the flow was going back and forth, and this shows from 0 to 360 degrees. And so it's a flow that didn't grow and was worked well with the periodic conditions, which I had in the code. And Onyalik and his guys were very successful with a Reynolds stress model in reproducing the skin friction versus the phase angle. So this is a pretty early example of DNS directly being used for validation of a RANS model, and a complex one. Okay, so one thing that happened is the log layer and the Kármán constant had been really hard to find in DNS. And then I want to discuss a recent theory of Lucchini, where he's looked at quad-Poiseuille and pipe flow, and I think did something extremely interesting. Okay, so I'm going back to my 1988 DNS of turbulent boundary layer, and up here I'm showing the velocity profiles at 3 Reynolds numbers, and at the bottom I'm showing y plus, du plus, dy plus, and that should be equal to 1 over kappa. And so here I put in the value expected. 1 over kappa would be about 2.5. And as the Reynolds number was increasing, then my results came closer, and I thought, well, this is very encouraging, although I did not have a long flat spot. And so in those days, you know, a long 30 years ago, we said we had low Reynolds number effect, and we will, it's too early to find the Kármán constant, but we'll do it. But the situation now is that the RE-tau Reynolds number has risen from 180 to over 5,000, and we're still not finding kappas. So things are not much better than here, and I'll show that. This is what I call the honest approach, which is instead of trying to fit a straight line here by hand, really looking for that quantity and looking for a region that is flat. I think I'll show. This is a figure of Lucchini at Reynolds numbers, about 500, 1,000, and 2,000. And this is the same quantity, so we're looking for a flat spot, and we're not finding a flat spot. And so even though going up to 2,000, but even at 5,000, we're still, DNS is still not finding the Kármán constant. And one thing that's been a real concern over the last 10, 12 years is that it seems that the pipe flow experiments at high Reynolds numbers lead to a Kármán constant of about at least 0.41, and the boundary layer more like 385. And so some people wrote papers and they said, well, maybe kappa is different. I think if the Kármán constant were different in a pipe and a boundary layer, it means that the theory just doesn't work. Also, I don't know how I could get a turbulence model to have that behavior. So I'm hoping that these papers are just wrong. And so, again, that figure, and so there's no plateau. And if you look at the regions where it's a local maximum, it's much too high. It's more than 3, and we're looking for about 2.5. So the other thing Lucchini pointed out, and well, people had found, is that if you plot that same quantity again in quad flow, plane channel, and pipe, then they disagree near the center of the channel, but they start disagreeing even before y plus of 100. And so these are all DNS results at the same Reynolds number, and they seem to show that the 2-3 flows don't agree well enough. So the disagreement around 100 is already very noticeable. So Lucchini went to work on this, and he had a paper in 2017 and one in 2018 that I find very interesting. So it's not theory from first principle, but here's a correction of the 3 flows that is the same correction for all 3. He also has a way to extrapolate from 2 Reynolds number values to infinity that is more mathematical than most. I think I have that. Yes. This is an example, I think, probably in the channel, in which he took results at 1,000 in red and 2,000 in green, and then extrapolated to infinite Reynolds number from that in a way that was systematic. And you see that now the profile of this quantity is much, much flatter. So that's already a progress, although it's still not flat enough to really give you an accurate value of kappa, and I'll come back to that. But this is the first thing Lucchini did. And then he adds a correction to the velocity profile that is some constant times the pressure gradient in wall unit times y plus. And in a channel, so it's proportional to 1 over RE tau, so it goes away at higher Reynolds numbers. Now this is arbitrary. There's no strong theory for that. So it's empirical, but you'll see that it considerably improves consistency between the 3 flows and also across Reynolds numbers, and he has only 1 constant. So it's not, fitting 4 flows with 4 constants. He's fitting 3 flows and a range of Reynolds numbers with only 1 constant. Now, I've had a disagreement with him because in turbulence models, I've always said you shouldn't use the pressure gradient because pressure does not influence vorticity. And I have articles about that, and I have ongoing discussions with him. And the steady flows he's doing, the pressure gradient is equal to what we call the turbulence force, which is divergence of the Reynolds stress tensor. And I prefer a term based on that. So I think we can use his theory and his A1 constant, and here we could use the turbulence force. I cannot say that he agrees with me yet, but there's chance. And some work of Gary Coleman suggests that in the flows where these 2 quantities are not the same, that one is a little better, but it's not published, it's preliminary. So you have seen this figure. Okay, so this is an example of Lucchini's correction in the pipe flow. So these are super pipe velocity profiles of McKeon and Altmark and Smits with a correction. So without the correction, there's what we call the wake region, where the velocity profiles go, and it's normal. They go higher than the log law. And once you apply his correction, and what's interesting is, this is a correction that's applied to experimental profiles that tend to be noisier. And it looks like it's bringing everything in really good agreement. So this is a case where Lucchini's work is taking away the Reynolds number dependence. Yeah, this is another one of his figures. He's trying to justify correction that's proportional to 1 over RE tau. So he's plotting here the velocity profile, the velocity value at y plus of 50 versus 1 over RE tau, and looking for linear behavior in different DNS of there's Lee and Moser and Hoyas and Jimenez, and I forget who the D is. But anyhow, the agreement between the different DNSs is not perfect, but it's pretty convincing. So he looked for support for the idea that 1 over RE tau was a good way to scale the Reynolds number effect. But just as a reminder, this is a conjecture. It's not coming from first principles. And now, here I'm showing the 3 flows, quet flow, plane channel, and pipe. And so you had already seen the difference here. And this is after his correction. And they get very, very close to each other at the same Reynolds number. And so, So now it's starting to look like the three flows want to have the same log law. So we're not going to have different Kármán constants in different flows. And so in this figures, I would say the three flows are essentially unified. Now this function, you get very close to a flat spot here. The only thing that is still a problem is if you magnify this region, and then you start seeing noise because of derivatives, you see that the Kármán constant is still uncertain to almost 10%. And what Lucchini is saying is that now we need to run the DNS codes longer to get rid of the noise. But he has a figure here where he argues that all the velocity profiles should kind of fit a straight line that intersects zero, z equals 0 at the same place. And what he says is 2.55 is the best estimate. And that corresponds to a Kármán constant of 0.392. And 0.392 is very plausible. It's definitely between the boundary layer values and the pipe values. So it's a value that, might be really quite a good one. Okay, so I think we may be getting over the problem of DNS not finding the Kármán constant, which is going to be really important. So next, I want to talk about these structural conflicts in RANS models. And I will show mostly comparison with DNS for the log layer behavior and the flow Reynolds number behavior. And everything I'll show will be in boundary layers. And the reason for that is that in the DES school of thought and many of the hybrid RANS LES, we think we're going to be using pure RANS only in the boundary layers. So on the cylinder, it would be in the front, and that all the separated regions and the more complex regions will be done with LES. And so if we're looking at the future life of RANS, boundary layers are really probably the last place where we'll use it, but a place where it's extremely important. So I'm going to show some channel and boundary layer results. This is busy. It's a figure I got from Ramsey at the turbulence modeling resource. I convinced him to go and run all the turbulence models at very high Reynolds numbers, partly so we could get the Kármán constant of all the models, and then some interesting things came up. So this is a Reynolds stress model at very high Reynolds number. Two equation models will do the same. You'll see that K plus is 1 over square root of C mu. So this is a log of Y plus. So we're going here from the wall to the center of the channel. And the Reynolds number is so high that there is a pretty wide region where the shear stress is equal to -1. I mean, -1. And so this is the log layer. This is the region where the shear stress is equal to the wall value, and the velocity profile will give a log layer. And now what's really interesting is that, so the shear stress is constant, but the other stresses are also going to constant. And for instance, and this is K plus, you see that it's constant, and this is not what DNS shows. And so I call this a structural conflict because all the RANS models are going to give constant Reynolds stresses in the log layer, and real-life DNS or measurements doesn't do that, and we're going to have a lot of trouble catching up with this. And what's really happening is that the models are just driven by the production term, which is proportional to the shear rate, du dy. And this obeys the law of the wall. And so U tau controls all the stresses, so they're all going to be proportional to U tau and not depend on y. So we have d tau ij dy equals 0 in this region. And again, it conflicts with DNS and experiment. Now, the question of plateaus on the Reynolds stresses, some people think very high Reynolds number pipe experiments see plateaus, but I think it's still controversial. So maybe 10, 20 years, people will say, oh, this is correct, but the Reynolds number needs to be so large that it's even larger than a submarine. So this is the first thing that happened in the channel. And the second one I discovered about a month ago is, so now we're looking at between the two walls. So this is first wall and the second wall. And the red curve is a shear stress, and it's linear, goes from -1 to +1. And the log layer is hidden in here. It's hiding in the region where the shear stress is almost essentially equal to 1. So I'm now looking at the region that has a high local Reynolds number, but is outside the log layer and going towards the center of the channel. And what we're finding that's interesting is that all the Reynolds, so that the shear stress is proportional to y minus 1/2. So it's just a straight line that crosses 0 here. And all the other ones are also doing the same thing. So what this means is that this Reynolds stress model, which is pretty sophisticated model, wants to have a constant anisotropy. So dAij dy is equal to 0. And this might be convenient. We might be able to find, I found exact solutions in the log layer using this for the Reynolds stress model, and we might be able to find exact solutions in this region, which is nice. But again, it's not real life. You will see that this is not, does not happen accurately in real boundary layers. And again, this is happening because the model is driven by just du dy. And so again, U tau and y control the stresses. This is why it has a simple behavior. And so this doesn't mean that the turbulence models are stupid, if you want, but it means that they're rigid. There are some things that they will just refuse to do. And you know, some people say, well, let's use a deep neural network or something to adjust the model. But I believe that all Reynolds stress, all turbulence models of classical type are going to want to have a constant value for the Reynolds stresses, all the Reynolds stresses in this region, for instance. So now we're looking at the Reynolds number effect. Again, my 1988 data. And up here is the three Reynolds stresses, V prime, W prime, and U prime at 3 Reynolds numbers. And they're rising pretty fast. Each time it's factor of 2 in Reynolds number. And in the results for the Reynolds stress model, these are 3 curves where we double the Reynolds number, and then 3 blue curves and 3 red curves. The model over the same interval up to y plus of 50 says, I have no dependence on Reynolds number at all. And so I expect it's going to be extremely difficult to teach any RANS model this behavior. W prime is the one that's the most sensitive. You see how much difference there is for just doubling the Reynolds number. Other things that near the wall, for instance, the wall value of dissipation or the pressure RMS, they're not constant. So there are lots of things. Okay, near the wall, the velocity profile obeys the law of the wall. So everything in the velocity profile is the same at all Reynolds numbers. but the Reynolds stresses are not, and for instance, the wall dissipation is not, and all these things. And you notice that even the DNS shows a peak in the Reynolds, the intensity near the wall, and the Reynolds stress model doesn't. So in addition to the Reynolds number effect, qualitatively, the shape of the curve is really not very good at all. Now, physically, Bradshaw had a 67 paper called Inactive Motion and Pressure Fluctuations in the Boundary Layer. And I think, and he thinks, this is what we call inactive motion, which at a given distance from the wall is waves that have very long wavelengths. And later, Wilcox had a few words about that, and Durbin, that led him to the V2F model. It looks like V is much better behaved, and so what Durbin had in the V2F model was to try and capture V and separate it from the other stresses. What is amusing is one equation models avoid this issue because they only have the velocity profile and the eddy viscosity and the shear stress. They don't have the normal stresses. So half the time it's too bad that I'm not getting normal stresses from my model. And the other half, it's, oh, I don't have to worry about this. Oh, sorry. So this is near the wall. This is the same curves as the three Reynolds numbers, but on a log plot. And so as you increase the Reynolds number, the thickness of the boundary layer increases in wall units. But what happens is that, yeah, there's a change for large Y plus, but there's no change for small Y plus. And the only thing in the model that could come influence the model, the results in this region would be diffusion from there, but the diffusion doesn't seem to do much. Another thing I wanted to show is the figure from my old paper in which I have the three Reynolds stresses corrected to infinite Reynolds numbers. And you see that once you plot it versus Y over delta, the outer region, they seem to agree quite well, except near the wall, because there you get to finite Y plus. They agree pretty well with experiment also. But that illustrates that even the infinite Reynolds number limit does not have a very simple shape, and the anisotropy is not conserved. This is physical argument about the inactive motion, and that is interactions at a distance. So if we're looking at this point in the boundary layer, it's going to feel that there's a bulge coming in the boundary layer, or there's a valley in the boundary layer, or some things are happening, and these things are not local. But the needs of CFD are to have a model that only uses local information to formulate the equations. And so this is why the model at this point seems unable to understand how thick the boundary layer is. In addition, we have a wall, and so all these eddies that are coming have image eddies. And so what we really have is that the bulge is here. There's also an image bulge that is influencing this point. And Bracio's argument is that what is less reproducible in the turbulence at this point is the part of the turbulence where the wavelength is much larger than Y. These are long waves compared with the wall distance. Yeah, I've argued that the diffusion term was unable to correct the model near the wall. These are work of Stabnikov and Garbrook and figures. This is the SST model, the K equation, and the diffusion term is negligible. It's all production versus dissipation. And if you look at the omega equation, the diffusion term is significant, but it's really dominated by the wall region. You can see that it's very strong near the wall and then gets weaker. So I cannot say that there's no diffusion, but I think I can say that, say at y plus of 50, I'm not feeling strong diffusion from y plus, of more than 100 or, 1,000. And so it seems that the SST equations confirm the fact that the diffusion is powerless. Okay, so next, we said that DNS had complete information, so it should be able to improve complex models. So did that happen? Not really. A great advantage is that DNS provides any budget that's desired. And now in theory, each term in the turbulence model, say Reynolds stress model, is correct. It plays a correct role. And so then DNS giving us these budgets would be much better than experiments. In reality, we tend to have compensating errors in the models. And the professionals of Reynolds stress modeling agree with that. For instance, the dissipation tensor is often modeled as isotropic, even though it's not exactly that. And then the pressure term is used to compensate. But then what it means is that when you get honest information from the DNS, then you have to admit that there are compensating errors. And the truth is that the model budgets of the highest moments are empirical. They're not rigorous. And a friend of mine who refuses to, he doesn't want me to use his name, once told me Reynolds stress models have more truth and more lies. And I think they have many more terms, and so there's a lot of empiricism in them. And then there are concepts, for instance, the pressure terms. There's a rapid term and a slow term. And the DNS is never going to separate those two. So it's not helping you when you're doing that kind of thinking. Another thing that's important is some models use a wall distance, or the Yakilish model uses a wall normal vector. And these are not in the equations. So you can get all the information you want from DNS, but you're never going to have anything that tells you this would be a good wall distance term or a good wall normal vector term. Finally, and this gets more complicated, is some people got the budget of dissipation, even the tensor, from DNS, and that's dominated by small eddies, but the real models are dominated by large eddy quantities and mean flow gradients. And this is because the energy cascade arguments are not perfect. And this was already known very many years ago. But this also means that the budget of dissipation actually is going to be very hard to use to improve a Reynolds stress model. Okay, so now let's get to simpler models. So one thing that shocked me, 30 years ago, is that I calculated K and epsilon from my DNS, and I thought, good, I can make a better K epsilon model. So, true, this is the equation for eddy viscosity in K epsilon. So if this equation were exact, by getting a better K or better epsilon, I would have a better model. But the reality is that in the log layer, the dissipation is correct in the K epsilon model, but the K, I showed you how K was constant and equal to 1 over square root of C mu. C mu is not correct, and these two compensate, and then we get the right eddy viscosity. So the K epsilon model is going to give a good mean flow because it has a good eddy viscosity, but it's doing it by having the wrong K and the wrong C mu. And so a direct improvement of K epsilon from DNS is nothing simple. Now this is some work I've done with Coleman and Ramsey. We also did some with the Strelitz group in other flows. So we're looking at an eddy viscosity model, And these are quantities from a DNS. And so the Reynolds stresses and then the strain tensor. And you can define an effective eddy viscosity from the DNS. And so that looks like it would be really great because we could, this is a function of x and y, say, and then we could say, well, where do we want more eddy viscosity or less eddy viscosity? You can see this as a least squares fit of a scalar eddy viscosity, or another interpretation is the scalar eddy viscosity that would give the right production. So anyhow, this allows us to take a DNS and say, what is the best possible eddy viscosity at every point in it? So it's a local target. Now, the results to date are mixed. I'll show some results where we get a better eddy viscosity, but the mean flow improvement is not reliable. And some of it is what I'd call a norm problem. That is, you might get improvement in a large region, but it could be that the wall region is really what matters. And Paul Durbin helped us understand that a little better. So this is an example, Coleman's work. It's a separation bubble. I think these are probably vorticity contours. So we have a nice long boundary layer, and then we have a sealing and suction and blowing. So we have a small region of separation and then reattachment. And it's a DNS with pretty high Reynolds number. And in here, on a log scale, we're plotting the eddy viscosity from all different sources. So this is from the DNS. And so as the boundary layer is coming, the eddy viscosity is slowly rising because it's getting thicker. And then it rises right at separation in this region. Then it falls, and then it rises again. So it has two peaks. And most of the models, say K epsilon and SST, are going to have only one peak. So qualitatively, there's something that we could improve. And the SARC model does that. The SARC model, thanks to the curvature effect, is strong enough that we're getting two peaks. So when we first saw that, we thought, oh, wonderful. The SARC model is going to do a much better job on this flow. Even the Reynolds stress model didn't have it, even though it really has curvature in it. And so I thought, wonderful, SARC looks good on this new flow. But these are the results for, so the separation bubble is, the reversal is a little before x equals 0, which is the center of the suction distribution. And on the right, we're showing skin friction, and the DNS is the red dots, and none of the models are very good, especially at reattachment. Just when the SARC eddy viscosity looked really nice, actually it's not helping. And all the models have flow reversal a little bit too early. The Baldwin-Lomax much too early, but it's okay. And K epsilon, as is a tradition, does not want to have flow reversal. So this figure makes Baldwin-Lomax and K epsilon look not very good, but all the other ones, different versions of SA and SST, seem to do the same thing, even though the eddy viscosity, the local eddy viscosity looked really good in the SARC. On the left, we're showing the momentum thickness, and it's the same thing. All the models are to the left and up from the DNS for momentum thickness. And so this figure made it look like we had something really nice on eddy viscosity, local eddy viscosity, and then that figure shows the mean flow doesn't really feel it very well. So we're learning these things. We have something in our toolbox, but currently it's not done anything as exciting as I hoped. All right. So artificial intelligence. AI has made great strides in very difficult areas like translation. Even over the last 2 years or so, there's been great progress. And so everybody says, well, there's machine learning, big data, deep neural networks. We have to use this in turbulence modeling. And I think you could argue that RANS has stagnated for a long time. And I've been publishing papers in which I talk about the fundamental paradox of turbulence modeling, which is really because of this local formulation that is just, it's just not reasonable to expect local models to capture turbulence effects from a distance. But the value of RANS to industry is very high, so we will keep working on it, and we should definitely, I'm trying very hard to find ways to use AI. And not only do we have stagnation, but the SA and SST models, and the heart of these models goes back to 1992. They're not founded on theory or DNS. So there's logic in hoping that artificial intelligence will end the stagnation in one or two ways, maybe. So some people are hoping we'll get new thinking, new terms. Some people think AI could decide on a new term to put into the model, like you know, new derivatives, or use of vorticity instead of strain, you know, some new physics. And there's a big hi-fi TURB proposal we just submitted to the European Union, in which people want to say, you know, get rich new DNS data sets, and that it will, through artificial intelligence, give better models. A less ambitious goal is to just have better optimization of existing models over a wide range of flows. When I created the SA model, I basically adjusted 5 constants over 5 facts of turbulence. But if I had a big system of artificial intelligence that looked at 20 flows at the same time and tried to do the best in all the flows at the same time, I could, even with exactly the same number of terms, get a better model. Now, in terms of philosophy, it's debatable whether these new efforts should include historical modelers like Mentor and myself, or try and a clean sheet of paper, right? It could be that Mentor and I think like Prandtl too much, and that we need to stop thinking like Prandtl. So I think it's, I've been consulted a lot by artificial intelligence people, but it might be that the real breakthrough will come from somebody who does not listen to me. But now some of the clean sheet efforts violate invariance and have some pretty serious defects. So about half the literature, I think, is going to go nowhere. Another thing of interest is the mathematical symbolic manipulation of equations has not caused much progress. You know, 30 years ago, people would write a paper on modeling and they would say, oh, the algebra is too much to really apply this thinking. And now people can apply the, you know, can do the algebra, but it has not changed the models. And the more studies I read, the more I see that it's artificial intelligence, but there's still human intervention. The people say, well, I'm going to train the model on this new flow. And they say, well, I'm going to train it only on the wall region, not the outer region. I get a better model this way. So I still have seen very few, maybe no papers in which there was no human thinking, you know, old-fashioned. So we'll see whether this proposal gets accepted, and we'll see what we can do with it. So to summarize, we've had DNS of wall-bounded flows since the 1980s. The Reynolds number has shot up from 180 to 5,000. In cylinder Reynolds number, we see results approaching 1 million and some wonderful work in Barcelona. We've had more geometric complexity, turbulent boundary layers, cylinders. There's DNS of golf balls. It's the largest sports flow where DNS is accurate. We have now flows with high Mach numbers and shock-induced separation. I still think the impact of DNS on everyday turbulence models is invisible. And the big reasons are the empirical nature of the models, the compensating errors even in the more pure models, Reynolds stress models. I've presented what I call the structural conflict or inability of RANS models. So that's going to make it very difficult. People are going to say, well, let's make the model agree with DNS. But the model is going to say, just refuse to do that. It's almost the same as what I've called the fundamental paradox. It's not the failure of, the invisible fact is not that DNS and RANS communities ignore each other. I've done both, and many people are doing DNS and really listen to what the needs are of the RANS modelers. Now, the value of RANS to society really justifies sustained efforts. In my mind, breakthroughs are not going to happen. Artificial intelligence might help, but it's still very immature. Another thing I'm finding is developing young people to do RANS modeling is really not easy. I think the new generation of people is, honestly, I'm not seeing it. And of course, I don't have students being at Boeing, but I've written a lot of papers, and I was hoping maybe to see more influence. But right now, the only group that seems to be really dynamic is in Darmstadt. Okay, so thank you very much.